Hello everyone, my name is Adam Ścibior. I'm a co-founder of Inverted AI and a postdoc at the University of British Columbia, and it is my pleasure to present Imagining the Road Ahead, joint work with my collaborators at both those places. We're dealing with the problem of trajectory prediction, so very briefly the problem statement is we have a map and historical trajectories of some vehicles. The goal is to predict where they're gonna be in the future. We're working in particular with the interaction dataset, where we're given 1 second of history and predict 3 seconds into the future. The time step is 100 milliseconds. And you'll note that the colors in the visualization change after 1 second. This is very much deliberate and indicates that this is the end of history, and from that point on we start predicting. There are all sorts of existing approaches to the trajectory prediction task. The crucial distinction between different approaches for our purposes here is whether we do one-shot or sequential. So in one-shot, you combine all the historical data you have about the agents and the environment and code them, and based on that you make a prediction for the full trajectory of the agent. In contrast, in a sequential setting, you only predict 1 step into the future, consider interactions with the environment and other agents explicitly, predict another time step, and so on. So we're taking the sequential approach here, and moreover we're decomposing the predictive model into a policy and an environment. So the motivating idea for this is that the difficult part to model about how human operated vehicles move on the road is the human driving policy. So we know that people receive some visual observations and based on that perform steering actions. And that is the part that's very difficult to model, and we effectively parameterized it by a neural network and learned that. On the other hand, the basics of how the vehicles respond to those steering actions and what sort of visual input the humans observe, those are not that difficult to model. So those we encapsulate in a hand-coded environment. It's a very simplified representation of what's happening on the road in that context. Now, what's crucial for making this whole setup work is we make the environment very lightweight so we can execute it quickly and keep everything on the GPU. But crucially, we also make it differentiable, because effectively we're doing imitation learning here, and being able to differentiate through the environment really helps with the covariate shift problem. So we learn the policy combined with the hand-coded environment, and jointly those two together form a predictive model of trajectories. To build the environment, we use a few very commonly applied components. One is the kinematic bicycle model, textbook stuff, translates the steering and acceleration into the motion of a vehicle. 2 is the Birdview Rasterization. This is also well established in the literature as a means of providing input about the map and the other agents to a particular agent. So here we see in the top a particular situation unfolding in a fixed coordinate frame, and in the bottom row we see how different agents in the scene view the same scene from their own egocentric, ego-rotated perspective, where each ego vehicle is colored in red. The final component is the Variational Auto-Encoder. So we add some latent variables to the model, which allows us to predict not only the single most likely trajectory of a vehicle, but the full distribution over the possible trajectories. So in particular in this image, we see that we both have a multimodality of predictions, where the red car can go either straight or left, and within each of those choices, those modes, we see that different samples lead to slightly different ways of going in that direction. So putting those components together and some standard recurrent and convolutional neural networks, we obtain full ITRA, where every agent is its own variational recurrent neural network and they're all interacting in this shared environment. So let's look at some prediction results. Here are 8 maps from the interaction dataset, where we unfold the predictions 6 seconds into the future. Now we trained for 3 seconds, unroll for 6. You might expect in this sort of models, as you unfold them longer than they were trained for, you'll eventually see some drift that takes them away from the data distribution. That certainly happens, but it doesn't happen immediately, so we can definitely produce good predictions for 6 seconds. And that's enough to observe some interesting interactions and predictions. For example, here we see a vehicle overtaking another one, or the red car, we don't know if it's turning left on the roundabout or taking right and the exit. So we see a nice bifurcation of the predictions here. The numbers are looking really good. I'm not gonna dwell on that too much. We have average and final displacement error. And what's really exciting is that we also tried the generalization track of the interpret challenge associated with the interaction dataset, where we tried ITRA on maps for which no training data was even released. So you see here some visualizations of those examples. And we achieved mean ADE of about 0.41, which is roughly twice what we get on the training maps. So full details about ITRA and the associated experiments are available in the full version of the paper. It's already up on arXiv and has just been accepted for publication at ITSC. And we can spend the rest of the time remaining in this talk to just look at some examples of the sort of behaviors that ITRA can generate. Now, something we're very interested in at Inverted AI is populating virtual worlds with human-like driving agents. So, in fact, we have instantiated ITRA as vehicles operating in Carla. So let's look at some examples of how it performs there. And just to be very clear, we've performed no domain adaptation here. We've trained on the interaction dataset, predicting 3 seconds. And what you see here is what ITRA does in Carla. All the vehicles in all the visualizations are controlled by ITRA. So starting easy, almost empty highway, see sensible driving behavior, following lanes, changing lanes, all good. Right? Moving on into the city, vehicles driving side by side into lanes, again lane keeping, and on the bottom you see Tesla successfully executing a lane change maneuver. Moving on to a more complicated setting on a roundabout, here we're doing a 14-second prediction into the future, and we see again ITRA is generating quite reasonable results. And you see that the cars don't exactly follow the lanes, much like humans wouldn't. Okay, let's move on to some more interactive scenarios. And in particular, just as humans do, we'll see ITRA agents actually breaking the rules of traffic. In particular here, we have the black car is failing to yield and forcing the oncoming vehicles to slow down. Here, watch the red vehicle. You'll see as the truck exits the roundabout, it decides to cut in a very, very dangerous way. So sometimes things don't work as well. So just to be very transparent and give you some bad examples, here is a bad prediction of ITRA where you see the green vehicle decides to go off-road for no particular reason. And for when things go really, really bad, it took me a while to find this example, but you'll see we've disabled collision physics here, so you can see exactly what's being predicted, but it's basically just total carnage. Everything is colliding with everything. On the other hand, sometimes we see ITRA executing some quite sophisticated maneuvers, so watch the silver car here. It's executing a pretty long-range maneuver to go around that cyclist and into the intersection. Finally, I mentioned that we're not just learning a single most likely trajectory, but the full distribution. So look at the order in which the cars exit the roundabout here. And now if we take another sample from ITRA, we see this time the bus is going in front of the small car. And similar here, watch the silver car going in front of the police car. Taking another sample, we see now the police car is going first. Alright, so it's a lot of fun to look at those examples. We could do it all day, but it's time to wrap up. So many thanks to my great collaborators, Vasilios, Daniela, Payman, Frank. Thank you everyone listening. Please come find me at the poster session or email me at adam@inverted.ai if you want to chat about those topics more. Thank you very much for your attention.